Okay, good morning, Chris Young here. Welcome back to N5 Physics. Today we're going to be talking about scalars and vectors again. Quick review of last time. What did we do last time? We did scalars and vectors. Yes, important difference is that, of course, a vector has a value of magnitude and a direction, whereas a scalar is just a number. Examples of scalars are speed, mass, temperature, things like that. Examples of vectors are velocity, force, weight, gravity, I suppose, things like that. So today we're going to be talking about scalars and vectors, especially, I don't know if you drive or not. How would I? You are multiple strangers. But if you do drive, then you'll know about speed cameras. Now there's two types of speed cameras. There's average speed and instantaneous speed. Instantaneous speed cameras are the usual ones, and I didn't know, but apparently on the way, when you're driving on the way towards a speed camera, coming up to it, that's when it fires out a laser to check your speed. And then after you go under it, then it knows to trigger the camera and take photos of you to get photographic evidence of your car number plate, and also it takes two photos very close together, two snapshots, and then it's got the time, and it can work out the distance because of the lines on the road, and then it can calculate your velocity. So I thought that was quite interesting, because most people usually slow down, well, after the speed camera. But yeah, I thought that was pretty cool. I mean, when they say instantaneous speed, there's no way to measure instantaneous speed, is there? You just have to get the time difference as short as possible. So it's like half a second or something, or 0.2 seconds. Then you've got average speed cameras, and I remember driving to the airport sometimes here in Scotland, at Edinburgh Airport. I think there's average speed cameras on that big curve. So it reads your number plate, the first one, and the time, and it knows the distance of the road, and then it'll check you again at the end. And as long as your average is under 50 miles an hour, then you're fine. So my question to Twitter was, can you can it along the motorway for like 100 miles an hour and then slow down to like 5 miles an hour before you go past the other average speed camera? I think you can, because it's average speed. It's an average speed limit, so it doesn't matter how fast or slow you go within that zone, right? Follow me for more driving tips. No, don't. Yeah, so you can calculate speed using things called light gates. If you want to do an experiment in the classroom, if you've got like a light gate connected to a computer, and if you drop something past the light gate to block out the light for a specific time, then you can calculate the speed of the object if you know the length of the object. Or if the object has a mask. I don't mean like a mask, I mean like a bit cut out is what I mean. Then you can calculate the speed of the object that way. I'd like to talk a little bit about bearings. For many years I was wrongly under the impression that bearings, zero was the front of the ship. Zero was forwards. You know when people say, "Oh, I've got a bogey at I've got a bogey on my 6." That the clock face in that situation is relative to the shape of, or the direction of the vehicle that you're in, or your point of view. But I thought bearings was the same. I thought 0 degrees was straight ahead and like 40 degrees was off to the right. But that's completely wrong. It's bearings is to do with the compass. 0 degrees is north. Doesn't matter which way you're facing. So get your act together, Chris. Come on. Vectors. The thing about vectors is direction is very important. So you need to define positive and negative. If you throw something up in the air, like this cherry, for example, then if you want to do calculations, you need to decide if up is positive or negative. Conventionally, people say up is positive, I believe, and down is negative. So gravity has a negative force on an object, and left to right. We in Western cultures read from left to right, so maybe that's why it's a convention to say that right is positive and left is negative. Also, that's how we draw graphs, isn't it? If you're like me, who is coming back to maths and science later in life, it may be a bit of a shock to the system to learn that you'll have to learn or relearn a word called Sohcahtoa. Sohcahtoa, of course, is not a volcano in Hawaii. It is a very useful mnemonic to help you remember, to help you work with triangles. So, S-O-H, sine, that means sine of the angle is opposite over hypotenuse, right? Ka, so ka means cos of the angle, so ka is adjacent over hypotenuse. Toa is tan theta, opposite over adjacent. Okay, and you've got your triangle here, right angle triangle. So, so hypotenuse is the longest one, isn't it? If this is your angle here, theta, then that's the opposite, and the adjacent is the extra one. Okay, so Sohcahtoa is very important, and also you need to remember about Pythagoras' theorem. Close personal friend of mine, a squared is b squared plus c squared. He must have been so happy when he figured that out, because he's probably spent a long time thinking about it. Or in this example, it would be h squared is o squared over a squared. Basically, the square of the hypotenuse is equal to the sum of the squares of the other two sides. All right, so this board here is your new best friend with vectors, because triangles are where it's at, dude. Because you need to calculate resultants and components, not only of directions and velocity, but also any vector works with right angle triangles, which is great. Well, there's two-dimensional vectors and three-dimensional vectors, and one-dimensional vectors, right? So imagine you're on a train, which is going this way at, let's say, 80 kilometers per hour, right? And you're walking this way as well at 4 kilometers per hour. All right, so relative to an observer standing on the road, what velocity are you going at? What speed are you going at? Well, you just add these two, they're both going in the same directions, just add them together, so it's 84 kilometers per hour you're moving in. Okay, it's all relative, that's quite easy. It's a one-dimensional relative speed problem. Now, imagine you want to swim across a river. Okay, this is quite an interesting one. So you want to swim from here to here, okay? But the river is flowing in this direction. So it's gonna mess with you a little bit. Let's say the river is flowing at, I don't know, 4 meters per second. And you swim at 4 meters per second. Okay? So you're not going to end up, you need to be careful, because it's going to push you this way, isn't it? You're going to end up over here. So what is, this speed, that's you swimming, and this speed, it's going to be, it's going to be the same, 4, 4. So what is your resultant speed? Well, this is where Pythagoras comes in handy. So a squared is b squared plus c squared. So a is the square root of 4 squared plus 4 squared equals the square root of 16 plus 16, square root of 32, which is let's see, 4 8s are 32, aren't they? That's 2 squared, 2 root 8. But 8 is also 2 times 4. That's 4 root 2. And I'm only doing it this way because in another video we're doing surds. So I've got surds all up in my brain. It's 4 root 2. So it's going to be 4 times 1.4, which is probably about 5.6. 5.6 meters per second. Is that right? Siri, what is the square root of 32?
That would be approximately 5.6568.
5.65? Wow! Okay. So I was pretty close with that one. 5.65. Right. Another thing that I found out about today was that when you're a pilot, if you're calculating vectors and speed and distance and all that, you have to take into consideration headwinds, crosswinds, because these are going to push you off course or speed you up or slow you down. So actually, it's a three-dimensional vector problem, flying, when you think about it. And air traffic control has their work cut out for them, that's for sure. They have to make sure that all the planes are flying in this three-dimensional space, and they're all going to like miss each other. So vectors are critical for them. I remember seeing a movie a few years ago. I can't remember what it was called, but it was this moment when there was a power outage at this airport, and all of the computers and phones just went off, and air traffic controllers were running outside like to get a public payphone to call the pilot. Oh man, and say, you need to change course and altitude to whatever. But I'm sure flying is still the safest form of transport. We've done speed cameras. We've done air traffic control. I think that's it. 15 minutes, right? We have to finish there. So that's it. I hope you found that interesting, and I look forward to seeing you next time. Thank you very much. Goodbye.